Hi guys, let me take a few minutes to show you how the handout involving the introduction to the normal density function can be used in order to make a simple model we call the empirical rule. So working with z-scores, if we have normally distributed data and turn those data into their corresponding z-scores, the mean is 0, and the standard deviation is 1. So we can break up this density function into regions by thinking about z-scores. So let's look at these z-scores specifically. So on question 12a of your assignment, you calculated using the shade norm command that 34% approximately of normally distributed data will have a z-score between 0 and 1. So now understand, this is a completely symmetric distribution. So that means that between z-scores of -1 and 0, you'll also have another 34% of the data. So we can confirm that by looking at the shade norm command or the normal density function on the graphing calculator. So if I use -1 for my lower boundary, so that's one standard deviation below the mean, and one standard deviation above the mean, if we look at the percentage of the data in the normal distribution, we get 68%. Well, that explains the 34% and the 34% that we just labeled on our model. So here, between two standard deviations above and below the mean, this accounts for approximately 95% of the observations in normally distributed data. So again, we can confirm that by using our calculator and the shade norm command. So let me use second program enter enter in order to clear the drawing. So from -2 to +2, we can confirm that the percentage of normally distributed data is about 95%. So going back to our model, understand 95% between -2 and +2, we've already accounted for 68% in the middle. So 95% take away 68% is 27%. And if we divide that 27% equally between these two regions, since the distribution is symmetric, 27 divided by 2 is 13.5% of the data. So within 3 standard deviations above and below the mean, recognize that we don't account for all of the normal distribution, but we account for quite a bit of it. 99.7% of normally distributed data will be within within 3 standard deviations above or below the mean. So we can confirm that here. Again, outliers can still occur. That's what's nice about the normal density function. We can certainly get values, they're not very likely, but we can get values that have a z-score above 3 or below -3. So, but for the purposes of simplicity here, 95% of our observations have z-scores between -2 and 2. That means these two regions or tails, far to the right and far to the left, account for a total of 5%. 100% minus 95%, that's 5% of the distribution. And if we divide that 5% in half, we have 2.5% on each side of the distribution. We typically call these tails. Now, what's nice about this model then is we can use it to represent normally distributed data. So as a simple example, let's think about the distribution of the heights of men aged 18 to 24. The distribution has a mean of 69 inches. So that's 5 feet 9 inches tall. So at the mean here, instead of a 0, I'm going to replace this with 69 inches. Now, I know the standard deviation of this distribution is approximately 2.5 inches. So if I go to a z-score of 1 or one standard deviation above the mean, 69 plus 2.5 is 71.5 inches. If I go another standard deviation above the mean, if I add another 2.5 inches, that gives me someone that is 74 inches tall. So 74 inches tall, that would correspond to 6 feet 2 inches tall. That's pretty tall. So one standard deviation below the mean, 69 minus 2.5, that's 66.5 inches tall, 5 feet 6.5 inches. Another 2.5 inches, another standard deviation below the mean would take us to 64 inches tall. So that's 5'4". So, but understand, if our data are approximately normally distributed, we can use this as a model in order to describe percentages within this distribution. So for instance, we could consider between what two heights do 95% of men in this distribution fall? So 95% of men fall between heights. Here I can see z-scores two standard deviations below the mean and 2 standard deviations above the mean. That middle 95% of the distribution is accounted for between heights of 64 inches and 74 inches. So for instance, I could ask the question, what percentage of men are, let's say, more than 71.5 inches tall? Well, 71.5 inches tall, that's almost 6 feet tall. 72 inches would be 6 feet tall, so this is 6 feet 11.5 inches tall. Either way, that percentage can be found by taking in the model this 13.5% plus this 2.5%, so that would make a total of 16%. Of course, another, I suppose, cheaper way to figure that out, instead of adding these two together, I know that half of men, so half of our observations are above the mean, that's 50%. If I take away the 34% that I don't want, 50 minus 34 is 16%, and that will give me the percentage of men that are 71.5 inches tall or taller, 16%. So you could even find a percentile with this model. So for a man that is 74 inches tall, what is the percentile? For a man whose height is 74 inches. So that's 6 feet 2 inches tall. Well, remember that a percentile represents the percentage of observations that are below that value, so that are below the 74 inches. So you could either add 13.5 and 34, 34, 13.5, and 2.5. You can add up all of those values, or the simpler way to do this is think about the percentage that you don't want. What I don't want is this upper 2.5%. So 100% minus 2.5%, that gives me 97.5%. So this is the 97.5 percentile. So that's a man who's relatively tall.